Hey, let's now open the demo day part of the event today. So this is going to be opened by Professor Kari Tammi, and in this part we're going to see presentations and demonstrations from our research groups who are going to present their latest research. So Kari is the head of the
you can hear me.
I can hear and see you well.
Okay, that's good. So yeah, welcome in Mechatronics Demo Day and welcome also in Aalto Industrial Internet Campus. So unfortunately we join online this time, but we'll anyway join. So we have 4 interesting teams in 2 parallel sessions in this Demo Day. They cover digital solutions in industry, enhanced hydraulics, rotordynamics, energy efficiency, and smart vehicles, just to name a few of those. My deepest thanks to all the contributors. Well, yeah, I started as Mechatronics group leader some months ago, and thanks to earlier group head Petri and the whole group, we really fly. We have like 3 to 4 doctoral theses completed every year, roughly 30 journal publications every year, 20 to 30 master's theses completed annually, and lots of teaching. Mechatronics Circus is one of our teaching outcomes. Today's themes, they reflect our research focus, but the contribution is substantially wider because of active industrial partners we are working with. So thanks to globally thinking domestic partners, we have a substantial international contribution in presentations as well. Some years ago, we started to research on digital twins, and I must confess, I was a bit afraid, are the results hand-waving only? And now I must say that I'm really happy to see industrial applications on digital twins, multitude of scientific papers published, and scientific openings on digital twins in all of our teams I mentioned earlier. In previous years, we have had this demo day, like a face-to-face meeting, and in those meetings we had more than 100, if I recall correctly, sometimes nearly 150 participants. And now we actually have more than 200 subscribed participants in this demo day. I hope you enjoy, and I also hope that next time we meet face-to-face. Demo Day 22. The organization of this event has required a lot. I want also to thank you organizers for persistence and pedantic attitude to systems and agenda and presentations. And I must say I really enjoyed Mechatronics Circus earlier. It's great to see such an enthusiastic attitude on research and learning. So thank you for joining, and I hope we all enjoy the rest of the day.
Thank you, Kari. So next we're going to have a presentation on digital twin web by Juuso Autiosalo. And Juuso started his doctoral studies on digital twins in 2017, and he's now in his final year. And the focus of Juuso's studies has been on conceptual understanding of digital twins in a way that feeds their practical implementation. And in the upcoming presentation, Juuso is going to introduce us to the concept of digital twin web, which is something similar to World Wide Web, but consists of digital twins rather than web pages. And the presentation consists of 3 main parts: current state of digital twins, vision of digital twin web, and suggested next steps. And Juuso, the floor is yours.
Okay. Thank you, Sam. Is my screen showing soon? Perhaps now, yeah.
Yeah, all's good.
Oh, okay, thank you. So hi, my name is Juuso Autiosalo, and I help people get rid of their mental blocks that say that digital twins should be complex, closed, or expensive, and inspire their minds to see the future of simple, open, and networked twins. In my presentation, I'm going to describe how these simple, open, and networked twins can merge with your existing solutions and how they will start forming a vendor-neutral network of digital twins, aka the digital twin web. So when I say digital twins are simple, I mean that the digital twin web gets its complexity from the amount of twins in the network, similarly as the internet here gets its complexity from the amount of computers and routers in the network. So during the presentation, as Sam described, I'm going to explain the current state of digital twins. Then I'm going to explain what we mean by this digital twin web and what are the next steps to get from the current state to the world where we have lots of these digital twins that form a digital twin web. I have also been developing an open source platform for this digital twin web, and I will give a teaser for that at the end of my presentation. So to the current state of digital twins. So when you ask, most people will say that origins of the digital twin concept come from a presentation by Dr. Michael Greaves in 2002. He called it then the conceptual ideal for PLM. And as we can see, it consists of perhaps three main parts: the real space and the virtual space and the link between those two. And then it also has these optional additional simulations for an alternative virtual space, but they basically mirror each other. And these links that they work, so you can check them out after the demo day when you have the slides. So at Aalto University, we have been working towards a more general definitions, a short one, as Greaves didn't provide a short definition, but our definition is that digital twin is a virtual entity that is linked to a real world entity. And it has these three parts: virtual entity, then a link to the real world entity. And that's common for all digital twins. And funny thing is that most definitions seem to be converging into a similar definition. Okay, this slide has quite a lot of stuff. It kind of resembles the digital twin itself. The point of this slide is that digital twins consist of many different technologies. We have 5G, whatnot. Simulation is very common example. AR, VR, communication protocols, OPC UA. And then I also have gathered some more origins of the digital twins. For example, the concept of digital twin was perhaps mentioned in the World Wide Web proposal by Tim Berners-Lee. not as digital twin, but as possible real world things could be possible nodes for the World Wide Web. It has not been utilized too much yet. Then some more interesting towards the present there's a paper that says that open source software is very important for digital twins. And also there has been developments on web-based twins. And right now there's two things that's kind of hot topics in the digital twins. Those are the multi-component digital twins. So digital twins that consist of multiple components, multiple different softwares that are connected to each other. I think we will see today at least one example of this kind of digital twin. And the other thing that is going on right now is this kind of meta-level descriptions of digital twins. So they are kind of text documents, machine-readable text documents that describe the digital twins. There is 3 examples here. The asset administration shell by Industry 4.0 people. Then there's digital twin definition language that's used in Microsoft Azure. And then there's Web of Things thing description by the World Wide Web Consortium. And these things, they have some things in common, but they also have their differences. And there's a couple of more kind of standards as well. So what we are seeing for the future of digital twins is that we will see some kind of standardized digital twin document. The standardized document is here in the center. It can include these or be one of these, we don't know yet. But that standardized digital twin document will provide links to each of these digital twin components. So take a technology and kind of plug it into the DT document as a link, for example. All right, that future thing brings us to the digital twin web. So here we have a digital twin or meta-level simple digital twin of a industrial crane. I drew it just as a simple kind of star formation. And what's important about that is that it is the one digital twin. It has a global identifier, and so it has global identity. Similarly, as I am myself and I have a social security number. They are not yet global, but Finnish government has given me a social security number. And well, that's kind of misused as a security thing, but really we can use, it's supposed to be just an identifier. But anyway, this is an individual digital twin of the crane, and that identity is very important because we are starting to create a network of these digital twins. So the crane says that it is located in a laboratory hall, and the laboratory hall knows that it has a crane located in it. And we can continue this further. Okay, no, I'm seeing that. Yeah, but we can continue this further. Laboratory hall is located in a building, and building is located at a street, and so on. We can continue to the whole Earth that's behind me. And of course, we can go it downwards as well. So crane has components. It has bridge and a trolley and a hoist, and apparently it has also a sensor attached to it. And of course, the laboratory hall can have a drill as well, which for some reason is also documented in the building. Not sure why, but those things happen. Point is that it's not a perfect tree format, but it's some kind of grid format. But as we go further, we start seeing more and more digital twins, and it starts to get more complex. But what's a bit more complex about the network is that this is just the first dimension of the digital twin web. So this network resembles or mirrors the physical locations of the digital twins. It's possible that not all digital twins have a physical location. So but I'm going to now explain a bit more about the other dimensions. So the crane is owned by Aalto University, and that's actually not dependent on the location of the crane or the location of Aalto University.
I'll remind also that session B is ongoing, and the link for that is in the chat if you're more interested in the topic over there. So I'm going to chair this session and introduce the presenters, and then Professor Karikami is going to be the moderator and manage the Q&A. So let's get started off, and we'll start off with a presentation from Pauli Salminen, and then we'll go through the other presentations that you see on screen. But let's start off with Pauli. And Pauli's a postdoctoral researcher in Department of Mechanical Engineering, and presently Pauli is working with the digitalization of mechanical engineering. And well, today computational models are widely used in mechanical engineering, and the next big step forward is digital twins and virtual models, as we saw a bit also in Juuso's presentation. In the near future, industrial machines and factories will have better user interfaces, which mix real machines with processed digital information. And Pauli and his team do research on these topics in the Machinaide project, which is what Pauli is going to present for us now. So Pauli, the floor is yours.
Thank you. So I will share my screen. Okay. I hope you can see it now.
That's great, Pauli. Excellent.
Thank you for the introduction, Sam. So I will present you our Machinaide project that has been running now roughly for 1 year, and we still have 2 years to go in this project. And I would like to present this project for you today because most of the presentations in this session and the following session are related directly to this project. Okay, so Machinaide is a relatively large research project with 90 partners among 4 countries. And it is mainly funded by ITEA, that is Center for Research, Development and Innovation. And we have here 4 countries: Finland, Netherlands, Turkey, and South Korea. And in this project, we are focusing on the smart industrial applications. So we have 19 partners, and these partners are coming from the fields of industry, making machines and software to operate the machines, and also research institutions, research centers, and universities. Our focus is to create better digital twins, to create seamless digitalization for the industrial platforms. So we try to create solutions to connect different kinds of industrial systems to create ecosystems in a similar way than, for example, Juuso Autiosalo explained in the first presentation. Then we also develop human-machine interfaces for the digital twins and industrial machines. And many of these machines that are connected by industrial Internet of Things. And then we also create applications and software to present processed information from digital twins and ecosystems to various users. The work in the Machinaide project has been divided in different work packages. To give some examples, Turkish consortium is responsible for running the work package 1, that's about use cases. I explain briefly Finnish use cases later on. Then we have interoperability between digital twin ecosystems, and we are responsible of this work package here in Aalto University. Then we have Dutch work package, processing of multiple digital twins data, and we are also participating in these work packages. And some of the presentations are related to this topic as well today. Then we have innovative human-machine interfaces for digital twins and services. And today we will also see an examples and presentation about this development. Then we have information usage across the machine lifecycle. And also sixth work package is about business models. And this is mainly run by VTT here in Finland, about how to make business out of this development. So an example about use cases. In the consortium, we have the idea of this kind of smart factory ecosystem where all the countries are connected. And if we take a Finnish use case as an example, we at Aalto are hosting this Aalto Industrial Internet Campus that acts as a focal point for development in Finland. So here we have some physical machines and a physical lab, and these are hosting also our virtual and digital twins of the systems. For example, we have a crane made by Konecranes, and then Roller Research International is developing their virtual grinding machine that's connected with the crane. And then we have Ideal and Remion developing software and applications, for example, and then VTT also doing research on business models. So I hope you do have now some better idea how the following presentations are related to each other and how these are related to this Machinaide project. And feel free to present questions, and I hope that our following authors can also reply some of your questions later on today. Thank you.
Thank you, Pauli. In the Q&A tab, there is one question targeted to you, but I think he's answering on it, and there is no question to you. Maybe again, I'll pose one. Can you a little bit elaborate this interoperability? What does it mean?
So the idea of interoperability is to connect different kind of systems. For example, if we have in our lab the Ilmatar smart crane and a virtual grinding machine from Research International, we need some ways to connect these machines to create one common ecosystem. How do these systems communicate and so on? So that's the main idea of the interoperability.
Okay, thanks, Pauli. Virtual applauses, and I'll move to Sam.
Okay, thank you.
Thank you, Pauli, and thank you, Kari. So over to our next presentation, if we can have the slide for the next presentation on the screen. So next we are going to hear from Joel Mattila and Riku Laurinhaho. I'm just waiting for the slide to come on the screen there. And they're going to talk about communication of a digital twin. Just to give an introduction to Riku and Joel. Joel has been working at Aalto since 2018, and he's worked with cranes and, for example, created an app for monitoring the crane and estimating its future usage. And his current research interests include the communication methods. He's currently doing his master's thesis about how the communication between machines could be implemented most efficiently in smart factories based on simulation and literature review. And so the following presentation picks up on his research interest towards communication methods and robot operating systems. And then for Riku, he's been working in the Department of Mechanical Engineering also since beginning 2018, and he's pursuing his doctoral degree. And his research interests include digital twins, industrial IoT, and communication between industrial machines. And in Riku's part of the presentation, he'll give an insight into OPC UA server and how it could be made more accessible by web APIs. And the presentation is going to compare REST and GraphQL APIs for OPC UA server. So, Riku, Joel, over to you for your presentation.
Hi, my name is Joel, and I'm going to talk about simulation of smart factory communication with ROS. So, as Pauli was talking about the Machinaide project, so one of the questions there is how the communication between machines should be done in the smart factories. So the research questions are how different machines and entities in smart factories should communicate, and what is the most effective way for communication. And the goal is to have some suggestion what is the best communication model for these smart factories. So first I'm going to go through a couple of communication methods, and after that how ROS will be used for simulating those, and in the end what are the next steps in this work. So first communication method is client server. So in client server there are dedicated client and servers, and here the communication goes so that the client sends message to server, and server responds to the client, and the processing in here is usually done in the server side, but it can be done in either one. And here in right, there are a couple of ways this can be done and could be done in the smart factory. So the first one is one where all machines are clients and are communicating with some central server that collects all the information the client sends them, and based on that it can tell the machines what they need to do. And the second one is the one where the client is this central system that will connect the correct machine depending what needs to be done. And then in the last case, the client is connects some server that then further connects to the correct machines that are servers. So in the last one, we can also see that the server side can have multiple layers, and depending on how many layers those are, they tells what kind of tier system it is in the server side. Then the next one is peer-to-peer. So compared to the server client, now every node is acting both as a client and as a server. So in this case, adding new machines will also add more processing power to the system, as all new machines can do some processing as they are also acting as servers. And these systems can be either pure or hybrid. So in hybrid case, which we can see in the top right, it has some elements of client server system where there's some central peer compared to the pure system where all nodes are equal and there's no central system. So advantage in this way is that the machines can send commands based on the sensor data they get, and they can also receive it from other machines compared to the first case where, because all machines are clients, they can't receive message, or they are servers and they can send message based on their sensor data. The last one is publish subscriber. Here in this system there's publisher, subscribers, and event manager. So here the publisher sends some data to event manager, and then it sends it forwards to the machines that have subscribed to that specific data. And in this case, all the publishers and subscribers don't know each other, and publishers don't know what subscribers have subscribed to their data, as all data flows through the event manager. And also this is asynchronous compared to the first two, as the event manager might not send the data immediately to the subscribers. And the subscribers can choose which data they subscribe for, based on its topic or content, or both of those. And Also, because this is asynchronous, it's important in the smart factory situations to inform that the message has been arrived, as it's not the default operation in this publish subscriber model. So what is ROS and why are we using it here? So it's a robot operating system, and it's a collection of different libraries and modules to creating robotic software. So the important things here are that it allows implementing communication between nodes, and we can also use it to add sensors to the nodes. And advantage with the ROS compared to some other systems are that it's very easy to share the systems made with it, and it's an open source system. And as it has a lot of modules, and one of these is the Gazebo, which can be used for the simulations. It's a 3D simulation software that has a physics engine. So with it, we can use actual sensor data then in the simulation and have box actually move, and based on those and the commands. So the next steps are creating actually these servers for these machines in a ROS, and then implementing these 3 different systems: the client server, publish subscriber, and peer-to-peer. And then the system where client server and publish subscriber are combined, so that the client server sends the commands and publish subscriber sends the data, like the position of the machines. And after that, running the tests with the ROS and comparing the bandwidth and ease of implementation, managing the communication, and then adding the digital twins for the help with the communication. And thank you for listening, and any questions?
Thanks a lot, Joel. Again, we don't have any question in Q&A. I'm wondering, do I get the update a bit later, or? But anyway, I don't see any question there. So I was a bit when we started to do this research design, I was a bit surprised that this ROS robot operating system works also in this type of application, because in my mind it is more like for autonomous robots or machines or robots in general. But but can you little bit like give further argument why you have selected in this application?
Well, based on the research, it seems to allow implementing the necessary communication, so the client server and publisher subscriber, and then also the adding the sensors, so they're for the simulation, so it should be easy to do the things that are, or get the results that are wanted here.
Okay, that's a good argument. Thanks, Joel, and let's move on. Sam, please.
Okay, so actually, Kari, it wasn't clear to me. Does Riku have a separate presentation here? I think.
Indeed, he has.
So I think I've introduced already to Riku. So let's pass over to Riku's presentation, and Riku, your floor is yours.
Thank you, Sam. It's actually planned that it's in the next session. So originally it was for me and Joel this presentation, but then we decided that only Joel gives this presentation because it's his master's thesis, so he can also check this master's thesis presentation with this presentation. So I will give the presentation in the next session.
Okay, all right. So all is clear. So you give your presentation in the next session.
Yeah.
Okay.
Thank you. Sorry for.
No worries. No. We see you back then, Riku. I look forward to that. So I think your presentation is coming back there at 2:10. So welcome back then. Okay, let's go over to the next presentation then, and this is from our research partners in Ideal GRP, and this is about a time machine for digital twin in process simulation. So this sounds pretty fun, and I'll give a short introduction to Harri and to Niklas. So Harri Taskinen. He's been working at Ideal GRP for 13 years, specializing in PLM for different companies and across several industries. And then Niklas has been working there in the same company since 2017, and he's specializing in creating simulation models of material flows, logistics, and processes within the Nordic countries and across several industries. And they will present on how to utilize multiple digital twins, historical data sources, and PLL information under one application. And that application is allowing the filtering of historical data to drive a plant digital twin. And the analysis is generating reports and key performance indicators based on the data and pushes them to the application. So, Harri and Niklas, welcome to give your presentation. The floor is yours. Thank you.
Ah. All right, so hopefully you can all hear me and see my screen.
All good, all good.
All right, so we decided to call this a time machine for the digital twin in process simulation, and we wanted to do it a little bit differently. So today you have basically with you two people. You have me, Harri Taskinen, and Niklas Busk, and there are other people also working on this. So who from our side is actually participating in this is basically we have Markus Ranta, who's the CTO of the company. We have Pasi Kallankari, who's the project manager, then me as the architect, and then we have two great manufacturing experts, Niklas and Fernando. And the company we come from is Ideal Group. It's a digital solution powerhouse. We are in Nordic countries and Baltic regions, and we specialize in digitalization, especially in PLM. And what we do with our products is basically we are doing digital twins. We are flowing the information through different domains from early R&D to actual maintenance, manufacturing, and performance, and doing analysis and simulation of everything. And the whole idea is that we try to do a closed loop system of the PLM environment, so the life cycle from the early R&D to the actual service execution. So that is what we specialize in. So with Machinaide, what did we actually want to do and how did we see it? So we saw it in a way that, like you have seen in previous presentation, there are a multitude of digital twins. And when people talk about digital twins, it's also a question, what are they really talking about? And we wanted to have them actually talk to each other. So we wanted to utilize information from different digital twins and wanted to make it sure that it's easy to understand. You can actually run it from one place, connecting to multiple twins, have everything, all the information collected to one place. And we also wanted to be able to run it from one device. So it shouldn't matter if you're working at your office or you're in a bus or using a mobile phone. So that was where we started. And we really wanted to have the information connected to it. So it actually is able to read from different twins directly the information. So how did we go about this then? We started with basic idea about how we see the digital twins. So usually our way of looking at it is if you talk about digital twins, we talk about early R&D, design, engineering, then to manufacturing, commissioning, and finally service. So how we saw it is basically you do it in a way that you have the product DNA where the ideas come from, then you do the design, you come up with a digital twin, which we usually do it in 150% way, and finally drive it to 100% production twin for manufacturing and commissioning. And finally, when it's running, you have the product performance twin. And the loop back in the PLM lifecycle, we try to connect the product performance back to the original 100%, 50% digital twin in design and have a feedback to everything. And how we do this is directly IoT and low code. And here you see the actual domains that are reflected. So you have the PLM in early past, then you have automation, mesh systems, you have ERP, and finally at the end you have PLM and service execution. So how did we apply this then to Machinaide? So we took a little bit smaller look at this. So in Machinaide, we tied it to the simulation, the factory digital thinner shots, line designing, automation designing, and manufacturing, commissioning, and finally the basically operation. And here we wanted to connect the actual feedback loop through these digital twins. So the actual from the process performance to the actual process digital twin. And naturally, the domains are very applicable to the previous one. And we wanted to do it with IoT and low code. So using either OPC code or then a low code application. So why? We wanted to basically start by understanding the basic needs, and our way of thinking is we want to basically add business value to just about everything we do. And we have been running this with Jira, so we basically started with use cases, and we have a multitude of them, and I took here a couple as an example how we were thinking about it. So we wanted to basically answer specific use cases. So you have cases like if you are a manufacturing process supervisor, you want to be able to replay the actual process that was happened. If something strange happened, you want to be able to view that, you want to be able to replay it and get an understanding of the process. And since we are connecting information from multiple places, we want you to be able to access from the one place. For example, if you're a service engineer, you want to be able to access the whole history of the actual service. You want to be able to get the current as maintained BOM from it to basically facilitate all the repair actions. So you don't need to wonder what is actually installed. You can just look in the app what is actually there. And we really wanted to have the capability of actually improving also the process performance. So you should be able to improve the process with this and analyze it. So that's how we thought about it. So how did we then go about this? We went about it by creating a plant simulation, to digital twin of that, and we created the low code application for the smart factory application, which is connecting to multiple places. And the reason for low coding is that it gives you basically out of the box interfaces to many applications, and development and maintenance is easy and fast. And it also is able to connect to the data centers we had at the moment. So we had access to MindSphere and we had natural access to Teamcenter data. So we connected to those. The smart factory application itself is built to be available and have basically the benefits of being able to replay it from anywhere. So, and what are we going to do next after this? We are basically trying to OPC, accelerated learning, basically allowing you to do what if scenarios, predictive maintenance. We are going to be looking into that, doing XR, and we are going to be improving the collision detection. You will see in a minute when Niklas does the demo, and we are going to be embedding visualization properly into the smart factory app. All right, so Niklas.
Yes, so this demo will show you how you can simulate real crane movements in a browser-based application. So to the left, you can see the application we have running in an ordinary browser. And to the right, you can see plant simulation. So in order for us to see better, we will start by just removing the roof. And here you can see the crane. And the crane consists of 3 different parts. We have the bridge, which is the large yellow part. On the bridge, we have a trolley that moves alongside it. And in the trolley, there is a hoist or a hook that is moving up and down. So when we when we want to start now, first we want to check that we are connected to plant simulation. So we have a connection status, which it says we are offline. So we will connect and see it says online, so everything is working. Then we want to select the time that we want to simulate. So we can select the start time and end time, and we will take all of the positioning data that exists between those two dates, so we can see what's happening. Additionally, we can also set some simulation attributes that we can see in the simulation. So we have a basic energy consumption and a drive energy consumption of the parts. We can also set a speed limit, which you'll see a bit later how we use that. And we can also position obstacles in the area where the crane operates. This is so we can see any potential collisions with anything. So here you can see we have positioned a KUKA robot in the area at a certain X and Y position. So you can specify that where you want to see it. And when we have entered everything we want to see, we can just send this information to plant simulation with the press of a button. And now everything is configured, so we can just start running. And now you'll see the simulation running and how the crane is moving. And so now the crane is then moving exactly how it was moving between these two dates we entered. And we can also see that we have some collisions with the robot. Then the robot will be highlighted in red. And when this happens, plant simulation will collect all of the statistics as to when and how long this is happening. So now the simulation is finished. We can just press, we can open a report where you can see information about what we have been doing. And here you can see the main data input. So these are the positioning data of the crane, of the different parts. So the first date you see, that is the start date that we entered, and the last date is the end date. So yeah, here you see all of the positions which we will move to of those crane parts. And in order to move to those positions, we need to set a certain speed of everything. So this is another result. So yeah, here you can see all of the speeds required for the different parts. And then you can also see the different speed limits that we entered. So here you could see, for example, if we have been running the crane too fast, maybe that could indicate if we have any problems or so on. So that's kind of those kinds of analysis you can do with this type of information. And we can also see, we'll just scroll down. Yeah, so here you can see all of the recorded collisions that appeared. So we can count that we collided with the robot for a total of 5 times. So what you can do with this is that you can run the simulation again, where you position the robot somewhere else, so that you can try to minimize or completely avoid all collisions. And we can also introduce more obstacles if we want. And finally, you can also see the energy consumption. So we can see the total amount of energy required to run the crane, and we can see how much energy each part of the crane will require. So that was this demo. So if you have any questions, we are open for them now.
Thank you, Harry and Niklas. Still, I have a luxury of stating my questions, since the questions and answers tab is empty. So can you a little bit explain how easy or difficult this is? Like you know, if you have like a blank paper and then you have to do this on factory, what type of data you need, what type of tools you need, how to integrate them all, and how big job it is?
Well, if I start, basically the plant simulation part, that is bread and butter for guys like Niklas and Fernando. That is that should be quite easy. The application part itself, where we wanted to have the interfaces, that is the low code part. And we didn't mention the low code we used. We selected Mendix for that, and it comes to really with out of the box interfaces. So as such, it's not that hard to do, but there is a little bit of a learning curve for that. Once you get past the learning curve, things get much easier. So overall, I wouldn't say this is extremely difficult, but it is not easy. You need some coffee and breaks to do this, but otherwise we are not talking about huge rocket science, but it is definitely doable, but it will take you some time.
Okay, thank you, Harri and Niklas. I'll move to Sam, please.
Development engineer at Konecranes, and Valtteri's presentation is about the future of crane digital twins and their connectivity with ecosystems. And a short introduction to Valtteri. So Valtteri has been working there in Konecranes since 2012, and his main tasks are concentrating on reliability of cranes, crane lifecycle data, and digital twin development. And in Machinaide project, he's been leading the Konecranes work related to digital twin use cases and connectivity to customer ecosystems. And so his presentation is going to give an overview of crane digital twin development and the customer needs for digital twin data and connectivity. So Valtteri, the floor is yours. Thank you.
Thank you, Sam. Okay, sharing my screen. Can you see my screen?
Yeah, it's all good.
Okay, and then I will. Okay, hello everyone online. I will tell you today about how crane digital twins look like today, how is their future looking like, and what are the customer needs for crane digital twins and their connectivity. Going straight to the topic, what we actually mean in Konecranes when we are talking about digital twins. It all starts with all the life cycle data that we have from our products through the life cycle. So the digital twins are a representation of all that data that we gather during the 20 years life cycle of a crane. So it starts as a digital shadow when we are selling a new crane, and it develops towards the digital twin during all the steps shown here. So first we have all the customer data from the sales cases and the customer relationships. Then from the PLM system, we get all the design item data, 3D models, other product information. Then when the crane is actually manufactured, we get from the ERP system all the bill of materials, serial numbers for the components, and the as-built structure of the crane. Then when the crane is delivered to the customer, we start collecting the usage history of the product. So we have the TrueConnect remote monitoring system, which Konecranes has developed. There we have the condition of the main components, the usage of the crane, and the alerts and production information. And then also we have the crane service, which gathers all the maintenance task information, measurements, photographs during the life cycle of the product. And all that data flows to the digital twins that we are currently creating. And Konecranes has this great platform called Asset Hub, where all the digital twins live and develop through the life cycle. So the digital twin is a connection point to all the source system data that we have developed so far. And to enable this, the whole pipeline of the data has to be in order and complete. So like I explained, it has taken quite a lot of work to develop this. So for example, the TrueConnect remote monitoring has been in use already over 10 years. And same thing for the maintenance reporting system that Konecranes uses. So it has taken time and a lot of work to enable all the high quality data from the source systems. And now, of course, to have this kind of a center part, the Asset Hub, that's also a big work to do, but luckily we are already having it now after the development and improving it continuously. But of course, there are a lot of challenges still related to the digital twins. So one big challenge is to create this kind of a work culture where everyone understands the importance of data, high quality data, and how we are actually utilizing the data and digital twins in our everyday work. So each of the stakeholders here who contribute to the data should understand the pipeline here and the importance of data and digital twins. Then another challenge is that there are some non-conformities between the source system, because the how the crane looks like as designed may differ from how it looks like when it's built and how it's maintained. So the as designed versus as built and as maintained is one thing to cover to enable this kind of a coherent digital twin. And then of course, different business areas in the company have different kind of needs for digital twins. Salespeople might want to have this kind of a 3D simulation model that Harry and Niklas showed, combined with the usage data to support the sales situation. And then maintenance business might have needs for a kind of like a asset structure combined with machine learning and maintenance history to improve this kind of a predictive maintenance activities. So then it's a matter of prioritizing the different business needs for the digital twins and where we should be developing them. But then what are the customer needs actually for the digital twins? What are the customers of Konecranes requesting to have from a digital twin? We have to remember that crane is always a part of a bigger process. It might be in a paper factory or a steel factory or a waste to energy plant, but it's always a part of something bigger than just the crane. But of course, it has a critical role in the connected and data-driven material flow inside the customer plant and process. So far, what Konecranes has seen from the customer field, what kind of digital twin data should be connected to their ERP or MES system. Some customers would like to have the production data, meaning that they would like to have the real-time operation status of the crane through the PLC and the OPC UA server of the crane, and also the material flow KPIs, like how many lifted tons it has done today, and how many work cycles to follow kind of like the production efficiency. Then some other customer may request to have the all the reported and scheduled maintenance tasks of the cranes in their system. So they would like to have everything from all the various machines in their main ecosystem. And then, like said about the TrueConnect remote monitoring, customers also would like to have the production errors and the alerts from the TrueConnect data to their own system, so that they are able to see all the crucial information from the centralized system, which is the customer ecosystem, which are now developing towards these smart factories. And what this actually brings to the machine manufacturer like Konecranes is that we should have some application programming interfaces to connect all the digital twin data to the customer ecosystem. So it's not anymore about selling only the physical product and some separate services which you can maybe use through a web browser or something else, but they would actually have all the crucial data in their own system. And that is what also the Machinaide project is aiming, and why Konecranes is part of the Machinaide project, to develop the capabilities of how to connect the crane and the digital twin data of the crane to the customer system. And then also, how does the future look like? There are different development needs and development paths that we are facing at the moment. One thing is to ensure that the digital twin really lives beside the physical product through the life cycle. If we now sell a crane to the customer, it will be in use for, let's say, 20 to 30 years. And there will be a huge amount of data coming from the usage monitoring and the sensors for the condition monitoring and all the maintenance history with the tasks and measurements and so on. So how do we keep all that data and the digital twin alive beside the physical product? That is one of the things that we have to really tackle and what we are working on at the moment. Then another thing is how we are dividing the digital twin functionalities between the local and the network or the cloud. So some functionalities can be implemented in the customer facility with the PLC and the OPC UA server and the gateway. So there we can have part of the digital twin features, but then there are some things that have to be done through the cloud and through the network, like handling a big amount of maintenance history data and usage data and applying heavier data analysis. So it all depends on the performance needs and the security needs that customers are requesting. And then as a third topic here, I had how to adapt to the development of the big IoT and cloud platforms and the digital twin standards, which also Juuso mentioned earlier. So there are some big players here in this field, like Microsoft Azure, building their platform and the digital twin definition language. Then there is Harri mentioned, there is the Siemens MindSphere as an IoT platform. Then also Amazon is developing their own services in this field. So which platforms and standards will actually spread in the customer industries related to Konecranes, and how should we prepare for those needs? That is something that we are also studying and trying to prepare in this Machinaide project. So there is still a lot of questions, even though we have already developed a lot in this field, and we have already a really coherent digital twin pipeline working. And that's why we are also part of the Machinaide project at the moment. And it really looks good and interesting from our side, how this is developing. Thank you. That was all that I have had today. Now, if there are some questions.
Thank you, Valtteri. And indeed, there are some questions. So thank you for also asking those questions. I don't have to ask everyone. So Tuomas Tiainen first asks, how do you identify which sensor data you store and which you discard?
That's a good question. So I'm thinking if I have a good answer for that. We are processing quite a lot of condition monitoring and sensor data, and also with the data processing, we are trying to identify which sensor values and data are in a way correct and high quality, because we have some rules defined to discard data which do not seem to fit into the correct thresholds. So let's say there is a monitoring for the usage parameters of the crane. If the usage parameter differs from the previous values from a previous day too much, then we will discard the data. Or same thing for the sensor data. If it's based on the rules, it doesn't seem like a correct value, we will discard it. And then, of course, we are trying to define rules how much data we actually need. Let's think about the vibration monitoring data. It's time series data where we gather, let's say, 5-second measurements each day. And if we collect that kind of data every 5 minutes, it will be a huge amount of data through the 20 years of life cycle. So we really have to think how much data we need for the purpose. If it's a condition monitoring related to vibration, we are quite sure that it's enough if we have, let's say, once per day or once per week, the correct measurements to monitor the trend line. But it really depends on the need and the use of that particular data. Hopefully that gives some kind of an answer.
I believe so. Yeah, we are a bit tight on time, but I'll read another question. Maybe you can answer very briefly. Joni Aro asks, are you aware of Asset Administration Cell AAS ideas, and do you find them useful? And then also like OPC UA information models, are they useful for you in future?
Yeah, the AAS is a term that I have heard, but I'm really not well aware of the purpose. But I know that inside Konecranes, there are the digital platform development team who are well aware of the features of AAS and how we should maybe take them into account. But I cannot really answer better at this point. But for the OPC UA models, I can say that Konecranes strongly participates in the standardization of the OPC UA model in crane industry. So it has been developing a lot during the past year in this it's a VDMA working groups that are developing the OPC UA models for different machine industries. For example, there are the robot industry where the more standards and models are already in use, and crane industry is also coming in near future in that sense.
Okay, thank you, Valtteri, and thank you, Jouni and Tuomas as well, and Sam, please.
Thank you to Valtteri, and thank you, Kari. Okay, so now we are going to pass over to a presentation which is shared by 3 of our colleagues, and it's going to look at the digital twin of a thruster drivetrain with virtual sensoring. So the opening words here will come from Jonni Keski-Rahkonen, who's working as a manager for technology and analysis for thrusters at Kongsberg Maritime. And then we will then have the other parts of the presentation given by Sampo and Jesse. So Jesse is a doctoral candidate at Aalto who's researching deep learning applications for rotor systems. And in this presentation, then Jesse is going to show some preliminary results from virtual sensor development project for ship thruster. And then sharing the presentation there is going to be Sampo Haikonen, and he's a research assistant at Aalto and has been building a digital twin test bench for torsional vibrations of azimuth thruster as part of the reboot project. So over to you all for your presentation. Floor is yours.
Thanks a lot and good afternoon, everyone. I assume you hear me.
Yeah, we hear you well. It's good.
Okay, perfect. Yes, so I can see my slide already. So my name is Jonni Keski-Rahkonen. I come from Kongsberg, and my part of the presentation is to introduce this predictive maintenance product that we at Kongsberg call Thruster Digital Twin. So what you see on the slide is, let's say, high-level description. We will go that through, and then Jesse and Jesse will take us next deeper to the actual virtual sensors and sensors development. So then how this actually works is that on the left side you can see our product Azimuth Thruster, and the first phase is that we have physical sensors as part of the Azimuth Thruster, and then we from the sensors we get data which further flows through the measurement devices to onboard PC that we have on board the vessel. Further, inside the PC we have software, and the first processing layer, the software is quality filtering, where we check that all the data is of good quality before we actually analyze it. And on the fly, next phase is virtual sensors, which basically are capable of showing what happens inside the thruster, even though we don't have physical sensors in there. So they basically show the loads and environmental conditions inside the thruster, and that's based on physics modeling. The next step on the line is virtual components. And these virtual components, they are capable of predicting their own remaining useful life. And further, they are also based on physics models. The next step is to save all the data on the local database. But one of the particular aspects of this environment where this digital twin is living is that it's on board somewhere out of the sea with the vessel. So usually the network is not that good. So bandwidth is very limited. Usually it's satellite network that is actually the providing the internet access. So we need to transfer a very limited amount of data over that network. And therefore we only transfer the most interesting summary information, which is basically the flow frequency data of the component remaining useful lives. In short, this is how the product actually works. But naturally, it's a rather complex one, and there is lots of research behind it. So I think Jesse will next take us through a little bit deeper into the sensors and how this actually works on that part.
Or actually, maybe Sampo, you can go ahead. You had a couple slides. Sampo, are you there?
Oh, can you hear now? Hello?
Yes,
we hear you, Sampo.
Yeah, okay. So yeah, I'm Sampo Haikonen, and I will now, before Jesse, briefly tell you about the digital twin test bench for torsional vibrations that we have built here in Aalto University. This test bench on the left is basically a downscaled version of Kongsberg's Azimuth thruster. And this test bench represents the thruster by having first engine and engine shaft, two angular gearboxes connecting a long shaft, and of course a propeller and a propeller shaft. Now, this test bench was built for the development of a digital twin. So we want to simulate multiple conditions of the thruster. And for that, we have a driving motor with which we are able to drive the system at various desired speeds. And on the other end of the driveline, we have a load generator, which represents the propeller part in the model. With this load generator, we are able to, it basically acts as a resisting excitator. We can generate any conditions that the propeller might face. And typically these are in our experiments being, for example, the propeller blades colliding with ice or the whole azimuth thruster rotating 180 degrees. And since this is a downscaled version, we wanted the torsional characteristics to remain similar frequency-wise. So we added two flywheel masses to the driving end of the driveline and to the propeller side. The engine shaft has also a flexible coupling to further reduce the torsional natural frequencies. And since this test bench has been used for simulation model validation and for virtual sensor research, we want to measure the states at multiple points of the system. And for that, we have 5 incremental encoders, which give us instantaneous angular velocities, and also the 2 encoders on the driving side and on the vertical shaft give us the torsion of the shaft. And lastly, we have equipped our system with 2 torque transducers for torque validation in our measurements. And now to you, Jesse.
Thank you. Share screen. There we go. So yeah, I am Jesse Miettinen, a doctoral candidate, working in the same group with Sampo. And we've been building this virtual sensor for the thruster. And basically, what is a virtual sensor? It is a computational model that estimates sensor readings from other sensor readings. And it can be useful if you might want to have less sensors in your system, or some sensor is broken. So you might have a resource to get secondary information from the sensor reading that was broken, basically. And if you want to build a data-driven virtual sensor, then basically it means you are using a machine learning model to do the same thing. And whenever you build a machine learning model, you need some data to train the model with, and then to test it. In this research, we've been generating the training data from a simulator built by Kongsberg and Åbo Academy, and then we get the test data from the test bench that Sampo just presented and built. And here are some preliminary results. The first three upper sensor readings are the input data for our virtual sensor, basically the encoders Sampo showed, and one torque sensor reading, and then the lower four are basically what our virtual sensor estimates, and the red curves are the virtual sensor estimates, and the right or the blue curves are what we have been measuring with the test bench. And we can see that it's somewhat accurate on the rotating speeds at encoder 3, 4, and 5. And there is some systematic error still at the lower torque, which is the propeller, near the propeller end of the motor. Here is some ice excitation, and we can see that it learns somewhat to estimate the ice excitations, but there is still some kind of systematic error in the virtual sensor, and we're still working on it. The y-axis is unitless because the data has been normalized, and these time steps here represent roughly 3 seconds of data. Thank you. Any questions?
Okay, thank you, Joni, Sampo, and Jesse. So Q&A tab is empty for this time. Maybe I'll then pose a question about this. It's mostly on this last slide, but I think it reflects back to the beginning. So obviously you can see that you have some higher frequency components missing from your estimated signal. Do you think it's a problem, or is it possibly a strength that you have already like pre-filtered your signal?
I think it might make the model more robust if we don't overfit on the high frequency components.
Okay, yeah. Now we luckily have actually 2 questions from the Q&A tab. So Ville Lämsä asks reasons for systematic errors in your. I believe it's the last plot here.
We've been having a conversation about it, and it's most likely due to some losses in the gears. So we train it with the simulator, and the simulator is slightly different to the test bench in a way that there are some losses in the torque happening in these gears.
Okay, good. And then the other question is how general is this virtual sensor term for? The question is by Markku Juntunen.
The term, how general it is.
Yeah, is it commonly known?
I think it's not very common. I think more commonly known is actually a soft sensor. If you look at the research publications, people use more soft sensors, especially in process industry. The soft sensor is more common, but I think in the industry, virtual sensor is more used.
Yeah, indeed, I agree, but I think you very nicely started your presentation saying that this virtual sensor is actually a piece of model or piece of software which is estimating a signal in one place. You cannot measure it for some reason. And this actually leads to the third question by Raine Viitala. He asks what type of savings you are possibly achieving by using virtual sensor instead of a physical real sensor.
I assume that it's firstly a good secondary information source if a physical sensor gets broken. And on another hand, there might be situations where you actually have a large sensor fleet and high risk of breaking these sensors. So you might be able to estimate the sensor readings without the economic burden of investing into a large sensor fleet in some machine. Maybe Joni has a more practical point of view on this.
Yeah, perhaps add a couple of words. First, I think it's very domain dependent. What is the savings potential using soft or virtual sensors? But in case of azimuth thrusters, the challenge is that the underwater part, it's rotating part. So you need typically some kind of wireless data transfer, which is difficult because it's typical Faraday cage. The other option is some sort of wireless transfer or sleeving ring type of data transfer out from the rotating part. And those kind of solutions, they tend to get either unreliable or expensive. So in comparison to the price of the product, I think the savings using these virtual or soft sensors are significant.
Thank you. Yeah, very good. I also agree, and I think there is a nice connection to the last question. I'm going to read. It's by Viktor Chichenko, and he asks the differences of the real system and then the physical model of the system. If you have different parameters. And you have actually always differences between the model and the real system. What you are going to do with the variations or differences?
Well, for example, if I understood correctly, that the system or the model that we use to generate the data that it might be different to the real world is the between simulation and real world. So in here we actually sampled 10 different systems with randomly selected components for the simulation data, and then we used basically 10 different mechanics of a thruster to generate the data, and then we tested it with the real data. So one trick is that you can do is to basically build varying dynamic systems in the simulator to make it generalized to many systems. Or yeah.
Okay, very good. Thank you, Jesse, Sampo, Joni, and thank you also for questions, Ville, Markku, Raine, Victor. There might be some interpretation error, so if you presenters might want to check and reply by typing some answers there if the question was interpreted in a wrong way by me. But thanks a lot for good questions, and I believe Sam has good news for all those who are waiting for break. So please.
Thank you.
Sorry, had my microphone off there. Yeah, thanks to Kari and thanks to Sampo and Jesse and Jonni. Yes, I don't know if I have good news because actually we've had really exciting and interesting presentations so far, but now there is opportunity to have a break. So we'll have now a 10-minute break. There will be an interesting video playing during the break. So see everyone back here at 1:10. Thank you.
How to find your purpose in life. 1. Create your calling. Don't wait for it. Do you want your work to be a job, a career, or a calling? Most of us would prefer having a calling. Calling is not something we're born with, but something we humans as meaning makers create. Let curiosity guide you. Feel, don't just think. You can spend hours, days, and years trying to figure out what the meaning of life is. To get a sense of which purpose resonates with you, listen to your intuition while working. Do I enjoy this? Does this inspire me? Pause for a minute and let your life speak for itself. 2. Transcend yourself. There are millions of purposes to be found, causes to serve, and problems to be solved in communities and organizations worldwide. Where are you needed the most? Get out there and explore. 3. Experiment. Don't overanalyze. How could you know if something's a fit for you if you haven't tried it out? You can start the experimenting already as a student by getting involved with different activities and fields of study. Each experiment will teach you something new about the world and yourself. Your purpose will reveal itself. How to find your purpose in life. 1. Create your calling. Don't wait for it. Do you want your work to be a job, a career, or a calling? Most of us would prefer having a calling. Calling is not something we're born with, but something we humans as meaning makers create. Let curiosity guide you. Feel, don't just think. You can spend hours, days, and years trying to figure out what the meaning of life is. To get a sense of which purpose resonates with you, listen to your intuition while working. Do I enjoy this? Does this inspire me? Pause for a minute and let your life speak for itself. 2. Transcend yourself. There are millions of purposes to be found, causes to serve, and problems to be solved in communities and organizations worldwide. Where are you needed the most? Get out there and explore. 3. Experiment. Don't overanalyze. How could you know if something's a fit for you if you haven't tried it out? You can start the experimenting already as a student by getting involved with different activities and fields of study. Each experiment will teach you something new about the world and yourself. Your purpose will reveal itself. How to find your purpose in life. 1. Create your calling. Don't wait for it. Do you want your work to be a job, a career, or a calling? Most of us would prefer having a calling. Calling is not something we're born with, but something we humans as meaning makers create. Let curiosity guide you. Feel, don't just think. You can spend hours, days, and years trying to figure out what the meaning of life is. To get a sense of which purpose resonates with you, listen to your intuition while working. Do I enjoy this? Does this inspire me? Pause for a minute and let your life speak for itself. 2. Transcend yourself. There are millions of purposes to be found, causes to serve, and problems to be solved in communities and organizations worldwide. Where are you needed the most? Get out there and explore. 3. Experiment. Don't overanalyze. How could you know if something's a fit for you if you haven't tried it out? You can start the experimenting already as a student by getting involved with different activities and fields of
Okay, welcome back, everyone. So let's continue with this session. So if I could have the next slide, please. Okay, and this just gives you the program of the remaining presentations this afternoon. So let's go straight forward to the first one and the next slide. So the next presentation is given by Joyce. So very kindly adopted an easier name for me to say here because I don't promise to pronounce your real name. And Joyce's presentation is going to be on a mixed reality interface for a digital twin-based crane. And Joyce has completed her master's thesis at Aalto, so been continuing her research here on creating innovative data-driven human-machine interfaces for digital twin-based services. And very specifically, her work is including is utilizing state-of-the-art mixed reality technology to operate an overhead crane called Ilmatar that we have in the Aalto Industrial Internet Campus. And in the presentation here, Joyce is going to give us a close look at her prototype application on the Microsoft HoloLens device, elaborating its setup, modularized architecture, and workflow with a demo video showcasing how it could empower a immersive, interactive, and flexible operational experience. Joyce, the floor is yours. Look forward to your presentation.
Okay. Share my screen. Okay. Sure, can see us. So hello everyone. Warmly welcome to Demo Day and my presentation. I'm Joyce. Today I'm really appreciate having this opportunity to share my work with you on the topic mixed reality interface for digital twin-based crane. So let's make a start by providing some background information. So nowadays, industrial production process is moving towards the new dimension of Industry 4.0, which is manifesting through convergence of many emerging technologies. It's especially characterized by introducing the digital twin, the digital representation of the physical assets, process, or system. As already covered in my colleagues' talks, you might already know that the digital twin could empower the whole product life cycle from machine design to development and optimization until maintenance with high flexibility and efficiency. However, the increasing amount of digital twin data within different formats and from different resources could also create a challenging context for the human-machine interaction, especially when safety and situational awareness are essential. Among many HMI technologies, mixed reality is acknowledged as a forthcoming evolution in the interaction among humans, computers, and the environment. The reality-virtuality continuum explains the concept of mixed reality, where both digital content and the real-world objects are visible for users through one display. And as a case study, we utilize the IMATA innovation environment located at Aalto Industrial Internet Campus as my virtual background, and conducted research on the CRAN platform equipped with the digital twin systems. Now let's directly dive into the prototype I built. So I draw this pic to illustrate the prototype setup, architecture, and the workflow. So the hardware and software setup consists of two parts. One is the Microsoft HoloLens One device and the corresponding software and SDKs used in the mixed reality app development as listed here. The other part is the CRAN IMATA and its operational environment, which embedded with its software system for the data access and the networking solutions. Based on this, the architecture and the workflow are formed. So overall, the users can interact with the CRAN in a bidirectional manner, controlling and monitoring through the MR application using HoloLens One devices. Within the mixed reality application, functionalities are grouped into two modules. They are interaction, visualization, registration, and communication. So the first one is the interaction model. It's with two functionalities. It's fixable and movable target control, where users can either select any of the four fixables in space or pick up and place the movables to navigate the CRAN. I will elaborate more like in the demo video later. The second one is the visualization model, which have three functionalities: a dashboard showing the CRAN status, target selection, and the communication status. The instructions appearing at the beginning of the application to provide new users with comprehensive guidelines, and the scene adjustment, which provides flexibility to customize the application layout according to user's need at any time. The third one is the registration model. This one is to enable the users to start using the application wherever they want, with the holograms always appearing at the correct and consistent positions relative to the physical world. So to align the virtual world and the physical space. To realize this, users only need to look at the image target, like the marker at the initial registration action. Last but not least is a communication model, which functions as a bridge between the CRAN and the other modules of the application. So here I will elaborate more about the communication model, as it's a key component for the HMI for digital twin-based services. There are different functionalities consist of this model in this specific application. One for input, the access code and changing the watchdog value, one for sending control signals according to the input from the interaction model, and one for monitoring the CRAN status and as input for the visualization model. And here we use the REST-Sharp API. API is used here to send the HTTP request to the GraphQL server. And also here, the multi-threaded behavior is also experimented out, where the three functions are running in different threads in a parallel manner. And also different settings of request frequency, size, and timeout experimented and selected to determine a decent communication performance for this application case. Here I will show some demo videos captured by the HoloLens device camera, so you can have a so you can have a test of the workflow from the user's perspective. So when you start the program, the instructions phase comes first. So you can first see the welcome page and it guides you to the registration phase. Once it's done, the holograms appears, followed by the explanation on them. And after this, you can either choose to directly start or go to check the kind of three-step guide on what you can do in the app. It's a bit low resolution from the HoloLens capture, but okay, the next one. So this is the initial phase. And this video starts with the registration phase. So once the green bounding box aligned with and stable, it means the registration is done. Like so, you align the hologram with the physical world. Then the virtual target will appear in the space correctly. You gaze and tape on the fixed board. Its color changed, and the crane will moving towards it. With also info on the dashboard updating in real time. And then you can also pick up the movable, then a special map merge also appears where you are navigating around the ball. And once you place it again, the crane will start moving towards it. Yeah. Stop it somewhere. Yeah. Also here, there is a scene adjustment interface. You can disable and enable different holograms. Like you can show the dashboard and like you can hide different targets, and you can like record the quick guide whenever you want. Yeah, that's basically it. Okay. Yeah, and this brings us to the end of my presentation. Thanks for interest and attention. Yes, I like to hear about your reviews and questions.
Thank you, Joyce. I'm reading the Q&A tab. There is none yet, but let's see. I'll have a couple of questions, at least myself. So this mixed reality, we can see it is clearly coming, and but there are quite many different applications, and first of all, I would like to ask you a little bit like comparison of different like mixed reality solutions, like you have AR, VR, you have different applications and so, but can you give some guidance like what type of applications are good for mixed reality, different types of solutions?
Yeah, so mixed reality is more like kind of, because you, like for example, for the HoloLens, you see through the glasses. So meaning that you are like really on site of the operational environment and you have some enhancement on the like the physical world. So normally it can like used for the kind of training purpose, like in the some enhancement and guidelines on the machines, and also it can like for some remote expertise support, like you can kind of have remote connections with mixed reality. So to distinguish, like for example, virtual reality as a kind of a bit different concept. So usually you are like rather than on-site, you're somewhere else. But this is normally for more kind of immersive experience, but you don't directly interact or control the machine in the way.
Thank you. And now there are actually several questions. So let's start from the last one because Sahin hasn't yet asked. So HoloLens field of view is quite limited in my experience, referring to Sahin. And how was your experience about the field of view limitation in industrial setting?
Yeah, I have the same feeling. Yeah, this like the also it's like the HoloLens one, so it's quite like it's kind of pioneer device at that time, but now they are more like kind of advanced devices, like which improve the field of view. It's indeed a bit of like it affects the user experience in the sense that because you see through, and also the frame of the glass itself like limited the user experience. So instead, for example, now there are this kind of video like streaming based mixed reality. So it can scan the whole space and you have like really good immersive experience in that sense.
Okay, and then Victor is asking about the main benefit of using AR in crane operation.
Yeah, so as I also said at the beginning of the motivation part, so they're kind of like for the traditional control the human machine interface, they're like usually you're either like with the panel or with the controller. It's of course can be even more accurate in that sense. But when you, especially when you have the deal with the digital twin based service and you are considering you have many different data resources and you want to really like give your immersive and interactive experience. So in this case, the MR or AR is quite beneficial in this case because like it can be hand-free and also you can directly project the information wherever you want in the space attached to the machine or the object or give some guidelines in a more informative and interactive manner.
Okay, thank you, Joyce. There is one question from Juuso about biggest challenge, but I ask you to type the reply in the chat because we'll thank you and thank you, the audience, and move on to Sam now.
Yes, thank you.
Thank you, Joyce, and thank you, Kari. Very nice presentation. Okay, our next presentation is from Miika Valtonen. Miika is Chief Technology Officer at Remion, and who's going to give his presentation on Scalable IoT data pipeline with Apache Flink and AWS on AWS. Miika is working at Remion. Remion is participating in the Machinaide project as an industrial IoT technology partner. Miika has a doctoral degree in IT. He likes to design modern industrial IoT data processing systems with AI capabilities. And in the presentation here, then Miika's gonna present on this data pipeline, and the pipeline was used to evaluate its suitability, costs, and scalability in a large-scale real-time data processing situation. So, Miika, the floor is yours.
Thank you, Sam. So good afternoon on my behalf. And as said, we will look today into this scalable IoT data pipeline that we have built on top of Apache Flink on AWS. And for some of you, this might not be, you might not be familiar with the Flink itself. So just a few introductory bits of that. It's a distributed framework for doing data processing at scale. And it can be used for processing large amounts of data from 100,000 or even million assets at a time. And it provides high availability for data processing, either in streams or batches. And it has a stack of layered APIs, so you can do the processing with Java or Scala, or using some SQL as well. It has some checkpoints, save points within its system, and it does all its processing in even time, so it really doesn't matter in which order the data comes in. And all this processing is done in memory, so it's really performant in its way, what it's doing. So the pipeline that we built with Apache Flink looks like this. And here on the left, you can see a data generator that we use to push in some data. And we generated data for 50,000 different machines of 3 different types. And they all provided 12 realistic signals, which had some abrupt starts and stops and signals going to 0 and everything needing correction in between. So it would be realistic that different cumulative signals don't, for example, work as nicely as they usually do in simulations. And we had these machines running on average 9.6 hours per day. simulating something realistic as well. And they delivered 14.5 kilobytes of data every 5 minutes to this ingestion stream, then next to the data generator, which one was actually run in EC2 instances on AWS. And in total, we generated 5.7 million messages per day, and we generated data for a period of 2 weeks when running this pipeline. Well, then in the Kinesis data streams that was used for the data ingestion, we had 8 charts in operation. And this data then from the Kinesis data streams that can be used with the Apache Flink for ingesting the data. And usually there's another stream then where the data is output. Here also Kinesis data streams. There could be also, for example, S3 bucket here and S3 bucket here where you can put the data in. But we use the Kinesis data streams for the easy purposes they provide when this Flink is run on AWS, and there they call it the Kinesis Data Analytics. So for the Flink processing here, we had an application that was developed and put in the S3 bucket, and from here deployed for the Flink. But Flink itself did the real-time processing with this pipeline, having 32 virtual CPUs computing the data parallel, and it also provides auto-scaling capability. And here we ingested the 12 raw data signals into it, and we got 8 KPIs out. So altogether, the KPI data and the filtered raw data going into the data output stream, which also had 8 charts in this hour specific, trying how to evaluate how this pipeline would work like this. And then the stream was split into 2 pieces. First, going upwards, here the Kinesis Firehose stored the data in the S3. So for the long-term storage, so that we can have the raw data always there available that the Flink processed, and also monitor the stream, that all the data that came to this output stream. And then the other stream went to the data consumer. That was a Lambda that batched the data, providing that data into the Regatta portal, in which the data was stored as a time series in InfluxDB and then in a MongoDB for the metadata. And that data was observable then from this Regatta portal front end. And some dynamic aggregations were done then on the data that was then available from the time series DB. So using this pipeline, we ended up with some data that looked like this in the Regatta portal. So having here one single asset with the data from the 50,000 assets, we calculated data in here. And in top here, you can see the filtered raw data, all these 12 different signals we got in from the Flink, and then the KPIs that were calculated in hourly buckets for different parameters. And here, as an example, you can see how we had in these hourly buckets the runtime in different states. So here in the blue, when the machine was idling, when it was moving empty or laden, and when it was operating a full hour, then there's a full bar of 1 hour here, and then when there's less, it's not full. Also, the hourly travel distance or the hourly fuel used was calculated by the Flink, and you can observe here the results for the single asset, but all this was repeated for the 50,000 assets and all the 20 signals altogether. So having deployed this application, run it in AWS, we want to know about the scalability of this type of an architecture and how it would perform. And here we performed a 24-hour stress test for these purposes. And we found out that these Kinesis data streams, as defined here with the 8 charts, we're able here at the ingestion path to process the data, one day of worth of data. And during this one day, when this data was processed, we were able to process 6.2 times data, so 6.2 days worth of data. So that equals that real-time rate. And in that 24 hours, we would be able to process 300,000 assets in this Kinesis data streams. Well, the interesting figure is then how much data in this time we could process in the Kinesis data analytics using the 32 virtual CPUs that could be scaled up though. And we found out that we were able to process 3.25 times the real-time data rate the data was coming in. And that would equal 160,000 assets communicating at real time. Well, then the actual bottleneck of this pipeline that we evaluated was found to be the Lambda that wasn't scaled up enough so that the data itself that was written to the Regatta portal and to the time series DB was 1.5 times the real-time rate. So that this would equal about 75,000 assets that could be processed real-time with this setup. So having deployed these tests, we found out that the demo architecture like this is really realistic and it could process real-time IoT data at this scale fairly well. And it could be still optimized and scaled up in AWS multiple times. So the scalability of this type of an architecture really isn't a problem. Well, also to see about the operating costs, we wanted to evaluate how much it would cost monthly to operate this. And these are the prices that we obtained for these services. For example, here we can point that it would cost about $1,000 for a month to process all these 50,000 assets and these 20 signals. And that would, in total, these numbers sum up to $2,400, and that equals about 5 cents per asset per month. So that's not really bad. And this excludes the data generator because that's not really needed in the actual data processing, and also the CloudWatch because the metrics and the logs can be adjusted to be some hundreds or even thousands of dollars. So it just depends how much logging and metrics you want to have. So we understood about the pricing, and that looks good. So in conclusions, we saw that the strengths of this platform was that the Flink provides a strong JavaScala-based framework or platform for processing the data in real time and at scale. And the Kinesis data analytics, which we used as a managed Flink instance on AWS, helped in commissioning and deployment of this system. And for the deployment, we used CDK, the Cloud Development Kit of AWS. KDA also seems to be fairly reasonable in the operating costs. And even though that we didn't do many optimizations that could have been done here, we believe that the costs could be significantly pushed down from the figures we showed you in the previous slide. But look at some weaknesses. Well, perhaps we could say that we need an analytical mindset and a strong coding skills to master these industrial IoT applications with Flink. And not everyone probably has these skills as, for example, we are doing. And also the best practices for the industrial IoT data processing are not generally available. So it hinders the adoption of the Flink. Well, to help this, we are looking forward to develop a Regatta framework for Flink to ease its adoption. So to bring in some additional tools that the actual Flink needs around it. So that some data processing libraries, templates, schemas, how you organize data, how do you communicate in different formats, how do you do the data processing when you do want to do it in batches again, do the reprocessing metrics, how do you do integration testing, and how do you deploy this into AWS. So make this more user-friendly for all people. So all in all, this is everything I had for you to share today. So thank you for your attention.
Thank you. Thanks a lot, Mika. So I got a question, actually, the weaknesses you mentioned. Do you think standardization would help some in let's say, short or medium term, or do you just have to live with I think some way the challenge is quite general in industrial IoT.
Mm-hmm. Yes, I believe sure that the standardization will help some, because the interfaces for example, the metadata that has been discussed today would be easier to fetch and use in the processing. So in this pipeline that we showed, we, for example, didn't show how the metadata was actually used in the processing.
Okay, and now there is a question in Q&A by Sahin as well. So how this compares with the Spark streaming? I mean, with Flink.
Yes, with Apache Spark, you will do usually more batch processing. So Flink is much more suited for stream processing of data and doing that with distributed machines. So that's the main difference.
Thanks, Mika. And let's move to Sam then.
Thank you.
Thank you, Mika, and thank you, Kari. So yeah, our next presentation, if we can go to the next slide. Our next presentation is by Tuomas Keski-Heikkilä, is a research assistant at Aalto, and who's going to give us a sneak peek on online high-dimensional modeling of industrial crane data. And Tuomas is currently doing his master's thesis at Aalto. He has prior work experience in production, maintenance, and process quality in industrial setting at Murata Electronics. And so this presentation is called a sneak peek. It's into his ongoing master's thesis, and where he's developing and testing a novel technique for multi-dimensional and real-time industrial machine data modeling. Tuomas, the floor is yours.
Thank you for the introduction. Can you?
So I currently see your slides, but they're in your own kind of computer view. Yeah, no, they're in slideshow view. Great, excellent.
All right, thank you. So I'm presenting my master's thesis, and this is indeed a sneak peek because well, we're past the halfway point in my thesis, but there's still a lot more to get done. So it's a sneak peek. And as advisors for this thesis, I have Mika from Remion, and then Riku from Aalto. But let's dive in, and first let's look at the research problem we have here. And if we take Ilmoter crane, for example, it records 96 variables, and well, some of these are duplicates in different units, and not all of them are interesting, but still high dimensionality is one key challenge we have. And then if you think about many applications you might have, like making visualizations from the data or perhaps anomaly detection, we prefer to get the data, results in real time, or at least as close to real time as possible. And then also finally, you want the modeling and visualization method to be scalable. Processing costs money, like we just saw in the previous presentation, and therefore you of course want to minimize the amount of processing you need. So all these 3 points put pressure on the method to be as efficient as possible. And now our proposed solution for this is multivariate fuzzy time series data model. And we're looking to study if and how these fuzzy methods can be used for modeling and visualizing high dimensional data. And then we are of course also interested if this type of modeling can provide added value for machine operators, engineers, or perhaps designers. And this approach is based on Miika's research at Tampere University of Technology, and it's now being applied at Remion as well. Now about the modeling method, we're basically taking advantage of multi-valued logic in our approach. And basically this means that there can be many truth values. And as an example here, I have, if you have, for example, 2,500 kilogram load, it can be heavy with a weight of 0.6 and can also be very heavy with a weight of 0.4. And in the method, we apply this to how we store and express the model. So all data is fussified using the fussification process. And here on the right, there's a few example fuzzy data rows where instead of precise values, we store the ordinal number of the membership function to which the precise value belongs to and with what weight. And then below you can see the graphical representation of these lines. So for example, for bridge position, you have 5 in both. And then as you can see, the 5th membership function is highlighted in green. And then for example, for trolley position, you have 2 and 1 with different weights, and they are respectively highlighted and so on. So now instead of trying to explain further how we do the modeling or how the fussification or defussification is performed, I'll try to explain why we would want to do this. So first, this way of storing data is more efficient. It takes less memory to store ordinal values than precise values. And then we can also reduce the amount of needed data rows with this method. And then fuzzy methods are also known for their processing efficiency. And then we can also apply semantics. The membership functions can be given descriptive names to increase interpretability. So for example, a load can be very light, medium, heavy, or very heavy. And then for example, for a trolley position, you might have a loading position and unloading position and so on. And then finally, when we have these membership functions, we have inbuilt aggregation in the system. So basically what I mean by this is that we can aggregate with respect to time or any other parameter just by selecting the wanted rows and giving them to the fuzzy system's defussification process. And from this, we can easily move to time series type of modeling by introducing time or other defining variables, such as maybe alarm data. And this way we can view the model in any state. And here in this animation example, I've added an alarm signal and time as defining input variables. And on the left, you can see the input variables, and then on the right, you have the output variables. And now in the animation, you can give different values in the input side, and you can see how the system has behaved. So for example, if you can give that, okay, when there is an alarm on and the time is between specific interval, how did the model behave? And then on the left, I have a few example data rows again. And there, as an added columns, there are now the defining variables, time and alarm. Next, I can show you a few visualization examples. So from the model, we can also produce visualizations of joint distributions. And this can be done with 2 or 3 variables. And then we have multiple different options for the type of visualization. So here, as an example, we have bridge position and then trolley position. And in the first picture, we have the raw data points of the path where we drove the crane. So we drove it back and forth in this L-shaped path. And then now this data and 13 other variable data was taught to the fuzzy model. And then we can produce visualizations such as these ones here. So one possibility is to draw a 2-dimensional heat map. And then in the third figure, we have a surface plot of the same data where the z-axis represents the density of the data. And then the main takeaway here is that we are able to produce accurate results with less data. So in the table below, you can see that the fuzzy model needs half the number of rows. And compared to the raw data model, and where the data is expressed as exact values. And then this combined with the fact that the ordinal numbers require less memory leads to 80% less smaller file size. So the same trend can also be seen when you look at the amount of data you need to make the visualization happen. So when we produce it with fuzzy methods, we are able to aggregate matching rows together in the database and only bring the aggregated rows to our visualization. And now another thing you can do is produce a prediction model to predict a certain amount of time forward. So, and you can do this recursively as far as you want to. So here as an example, I have a very simple cumulative machine usage signal, which we have predicted. And the signal has a clear trend underneath the randomness. And we can easily find the trend with the fuzzy prediction model. And basically in the learning phase, we store the state of the model and the state of the machine one time step after that. So now when this formed model is given some state as input, it gives the prediction based on all the times the same state occurred before. And then we get a precise prediction value using the defussification process. For a cumulative signal, we can't use absolute values for learning. So we have to model from differences between consecutive values. Now, as another example, you might have a sine wave. So here we can apply the same logic, but now we can also use the absolute values for learning. And then we can also see that the further we try to look a signal like this, the bigger the error will become. And for these simple signals, there's obviously better and other ways to predict, but the goal we have is to use this for more complicated and multi-signal systems. And now these prediction principles can easily be extended to anomaly detection. So instead of predicting the future, you just predict the current state, and then you compare it to the actual values that you might measure from the system. And then you can quantify this difference in absolute or percentual values. And well, finally, the findings so far, the results have been promising. We're able to produce accurate visualizations with the model, and the model needs less memory. And the first steps towards the predictions have been successful. And also high dimensionality hasn't been an issue with our 15 variable dataset of real data. But I have to say, if you generate like 10 random signals with no relationship to each other, then you quickly run into the curse of dimensionality. So this shows that for the modeling to be successful, there needs to be correlations between the signals. And then we've also found that the potential uses for the model are viewing the state of the model, visualizations, predictions, and then also anomaly detection. And for future work, there's still much to do with the model development, such as optimizing the membership functions, and then improving the fuzzy inference methods and so on. And then we also want to do the predictions with more complex signals, and then implement the anomaly detection, and finally find some practical use cases that we can try to, that this could be used for. And well, that's all I have prepared, and I'm happy to answer any questions if there's any.
Thank you, Tuomas. I got one. So you said that you nicely save some space by using fuzzy instead of raw data. Will you pay some price on processing demand or memory demand or so?
Well, there's of course, you have to think how much you do lose a little bit of accuracy, I think, when you do this, but I don't really have exact information to say at this point how much you lose on accuracy when you do the data reduction. But in our example cases, it seems that we can reduce it without really any downside.
Okay, very good and very interesting. Thank you, and we'll move to Sam.
Thanks.
Thank you. So our next presentation is from Thomas Wiedmeier, who's going to talk about virtual grinding machine. And Thomas is a project manager at Roll Research International. He's a grinding machine specialist, and he will present the use of a virtual grinding machine for grinding machine installation, commissioning, and future development. Thomas, the floor is yours. Thomas, we seem to be missing your sound. Seems that your sound is not working at the moment. Okay, maybe Thomas, if I could make a suggestion, maybe we try to fix the sound with one of my colleagues, and in the meantime, maybe we could then jump to the next presentation, and you could take yours afterwards. If that would be okay. So in that case, let's go to Rico for his presentation, and we'll come back to Thomas's afterwards. So I introduced Rico earlier, but I think I'll introduce again. Because we thought his presentation was rolled in with another one. So Rico has been working here in Department of Mechanical Engineering at Aalto since 2018, and is currently pursuing his doctoral degree. And his research interests include digital twins, industrial IoT, and communication between industrial machines. And so following presentation is going to give an insight into how an OPC UA server could be made more accessible by using web API. And the presentation is going to compare REST and GraphQL APIs for an OPC UA server. Rico, the floor is yours.
Thank you again, Sam.
Thanks.
Oh. Yes. Okay, so hello everyone. My name is Rico Laurinahan. There have been so many interesting presentations already today. Thank you for presenters. And in this work, there has been already also many people involved. So Joel Mattila, Juuso Autiosalo, Jani Hietala, Heikki Laaki, and Kari Tammi has helped me with this work. So let's go to this comparison of REST and GraphQL interfaces. So motivation for this was to provide an easy access for OPC UA servers. So currently, if you want to access the Crane OPC UA server, you first need to download and install OPC UA client. But with web technologies, we want to provide an easier way for this so that you can only use browser or libraries for HTTP libraries to access the Crane data. And another motivation to provide this easy access is to do faster application development, and this was confirmed that it's really needed already in the DigiTwin project. And Joyce also used this GraphQL interface to get data for her HMI application. So I will quickly introduce you OPC UA, because I think already many of you are familiar with OPC UA. So it's standardized protocol for industrial communication, and it's developed by OPC UA Foundation. It works with almost any devices, so from embedded systems to cloud, and with Windows, with Linux, and almost any device. It supports both client-server and public subscribe models, but in this work we used only the client-server model, in which OPC UA server provides services which we can use to read and access the data. And the data model of OPC UA is kind of graph or tree. So there are nodes which present variables or real-world objects or parts of machines, and then there are relations between those nodes, which describe the real-world like relationships. And REST is very popular way to implement web APIs. I would claim that it's like almost every web page uses REST to get data, and it's kind of describing the overall architecture in a web. So Fielding presented this architecture style already at the beginning of this century, and it has been used since then. And it's commonly used with APIs to provide machine-readable data. So, for example, this could be used with Crane to provide machine-readable data from that. And the basic idea of REST is that it uses HTTP, and clients ask some data, and then server returns that data to the client. And now about GraphQL. So GraphQL is a new way to implement web APIs. So it was published as open source in 2015, and it's query language and runtime. And the main idea is that only the needed data is returned. So for example, on the right there is this example query. So the name of the fields returned are specified, and below is the response. So only these fields are returned, which is very different from REST. And also multiple resources can be requested with a single request. And Jani Hietala implemented this GraphQL wrapper for OPC UA server, which was used with the overhead crane in his master's thesis. And now let's jump to the comparison between GraphQL and REST. So basically the communication model is similar, but GraphQL also offers this subscription model in which client can subscribe data from server. So when there becomes new data available, then server can push data to the client. And the protocol is also HTTP with both. Well, any protocol can be actually used with both, but in practice it's HTTP. And for subscription, WebSockets are used with GraphQL. Caching is one big difference between REST and GraphQL, because caching is possible with REST at every layer, because there is this URL which gives a unique ID to every resource. So then therefore it's possible to do caching at any point in the route. But in GraphQL there's no such thing, or it can be introduced, but it's up to the developer of the application. And because caching is easier with REST, therefore also scalability is better with REST. But some papers have actually showed that without caching, GraphQL performs better with multiple clients. And the biggest difference between REST and GraphQL is this uniform. So REST provides uniform interface, so it uses HTTP and its methods to interact with the resources. But with GraphQL, there is this schema which defines the possible operations. So it's application specific. And ease of use is, both are easy to use, but GraphQL offers this GraphQL tool, which basically is web interface to access the data. You can browse the data and do the queries with that interface. And ease of development is good for both because they provide, there are a lot of libraries available and many platforms are supported. And because GraphQL specifies the data, which is fetched, and then also multiple resources can be fetched with a single query, therefore the bandwidth usage is much lower with GraphQL. And this also reflects to performance. So performance should be better with GraphQL than REST. So I just quickly showed the measurement setup. So we had one laptop act as a client, then we had this GraphQL and REST API, and then we had OPC UA server. So when client wants to fetch data, it first sends request to this GraphQL and or REST API, and then this GraphQL REST API gets the data from OPC UA server, and then this GraphQL REST API returns the data to the client. And for GraphQL implementation, we use this solution by Hietala, and for REST interface, solution by Cavalier et al. These are both available on GitHub. And about the results, so OPC UA is significantly faster than REST and GraphQL, but REST is slightly faster than GraphQL with single values, and as expected, GraphQL outperforms REST with multiple values. So there's like 5 times higher request execution times with REST than OPC UA, I mean GraphQL. And about the payloads, the results were also as expected, but well, OPC UA has very low TCP payload size, but it's somewhat explained by the fact that there was no authentication used. And because GraphQL well specifies the data, which is fetched and can fetch multiple resources with a single request, therefore it uses less bandwidth than REST. And now about the conclusion. So it was shown that REST and GraphQL interface, they will add a lot request execution time, but this was expected because they're kind of extra interface, and they still need to do the actual OPC UA request. But they also increase the bandwidth usage considerably, which is a major downside. But however, these two interfaces provide some other favorable features like better interoperability and make the GraphQL, OPC UA interface more accessible. But for these two, we would select GraphQL because it offers better performance and lower bandwidth usage, and also this GraphQL tool, which makes it very easy to use. And we suggest that GraphQL interface is provided along with OPC UA because it's very easy to add just to be used with OPC UA server. This solution by Jani Hietala is basically just plug and play. So you just give the URL of the OPC UA server, and then it works. So it's very easy to use. So that is our suggestion that you should use both GraphQL and OPC UA servers. Okay, that was my presentation. So if you have any questions, please ask. Thank you.
Thanks a lot, Riku. There is in Q&A, there is one in by Jouni about communication security.
Yeah, communication security. So for REST and GraphQL APIs, we have JSON Web Token based authentication, but with OPC UA server, we didn't have actually any kind of security measures. So it is not secure at the moment. We should implement kind of secure tunnel between OPC UA server and the interface. And also these servers were not run on top of HTTPS, but it's something that can be done, but it was not done in this work.
Yeah, and a very good question. If I may comment, we did some literature review on digital twins, and actually there are very little commenting on data security, which is kind of like obvious challenge. So somehow still this is maybe more research than application in some cases. The other question is by Sakin, how does API discovery happen in GraphQL? And then he explains in REST spec the root route should list all possible resources.
Yeah, it's true that the hate OAuth constraint is violated often, but with REST. But GraphQL, it's basically that you need to know the ID of the node so that you can access the node. But because GraphQL can browse the OPC UA server, you can do the browsing of the OPC UA server from the web browser. So when you give the address of the OPC UA server, then you can browse the OPC UA server via GraphQL interface. So that's kind of the way it's easy to use.
Okay, thank you, Riku, Jouni, Sahin. Let's check what is the situation with the audio by Thomas. So I think Sam knows some further on it. I suggest we move on to Thomas's presentation if everything is working, but we may have a couple of more questions if not. But Sam, please.
Okay, let's just do a test if Thomas, if your audio is working now. No, it seems not. Okay, what we'll do is maybe if there are more questions to Riku, Kari, we'll try to sort out Thomas's audio in the meantime, if that's okay. We'll just take a couple of minutes there.
Okay, thank you. I'll look back a little bit what questions we have. I think that we also missed a couple of questions from the earlier presentations, but if you want to ask some further, Riku, please do so. I'm watching the Q&A, and meanwhile I wanted to ask Riku. There are also quite many other opportunities than GraphQL or so. There is this old joke that why you need so many programming languages, and the answer is that you can write hello world on the screen in different manners. And can you a little bit elaborate what other options you would have?
Well, actually, the major way to do this kind of APIs is in web is this REST API, and there is not so many alternatives to that. There have been some, of course, there are like plenty of small which are not widely used, but this GraphQL is now really coming. So, for example, GitHub and Airbnb and Twitter, all large companies actually nowadays have this GraphQL interface. So I wouldn't say that this is just another new interface. So this is going to be big, I think, this GraphQL. It has so many favorable features compared to REST, so it's really coming.
Okay, thanks for clarification. Now Sahin has a question. Is GraphQL a dialect of Gremlin?
I have to say that I don't really understand this question.
So I haven't heard this Gremlin language either.
But I can actually answer to Jouni Aro's question. So he asked, did you consider OPC UA WebSockets? It is not supported by servers very much yet, though. So we have actually written a Python library for the Crane OPC UA server, and we used WebSockets with that. But for this GraphQL and REST interfaces, we used the Crane, or we used actually only test OPC UA server with OPC UA over TCP. So with Crane, it's possible to use both OPC UA over TCP and over WebSockets. But yeah, with these interfaces, we haven't considered to use them over WebSockets.
Okay. So yeah, Ville and Sahin are sending links for further info for us. Thank you for those. I don't click them because I'm afraid that I will be led to somewhere else than this. I'll go a little bit back. There were a couple of questions. I think okay, I might have lost them, but there were a couple of questions I missed from the earlier presentation because of lack of time. But let's see how it. Yeah, there were actually for Tuomas there were a couple of questions. I'm not sure whether Tuomas is available to answer, but also Riku might know if Tuomas not available. So by Sahin there is a question: have you considered something like PCA, meaning principal component analysis for dimensionality reduction, and how does it compare with fuzzy modeling? So is Tuomas there to reply?
Yes, I am. I guess. Well, we haven't considered that, but I wouldn't compare the two because I see it more like you might still need to use PCA methods later when using the fuzzy methods if you have too many dimensions and you need to reduce them. I'm sorry, I don't have a better answer.
Yeah, I think yeah, but Sahin has a point. There are quite many ways to reduce the data, and this fuzzy seemed to be easy and straightforward. But like I think, for instance, like if you come from control engineering background, you might think about these principal components and so. Then Juuso is also asking Tuomas, is it possible to define the confidence of the predicted signals? So can you estimate your accuracy somehow?
Yeah, indeed. I answered it in text, but I can basically read what I wrote. So the prediction isn't, of course, very useful if you don't know the accuracy. But at this point, we haven't studied very much. But and we will likely need to experimentally try to determine some confidence intervals for different signal types. But from the example signals, you can see that, for example, for the linear cumulative signal, the error was about 5%. And then for the sine wave, we had around 10% error with a 100-step prediction. So
okay.
Ballpark, maybe.
Thank you. That was a good one. I'm checking my phone. WhatsApp is there, and let's check with Sam whether something positive is happening regarding the voice connection.
We were going to see if this will work with Thomas coming in to give the audio part by phone. I'm just waiting to see if that can be done.
He is just now calling in, so he will be here soon.
Okay. Do we have one more question in the line, Kari?
Yeah, maybe I think I exhausted those. Let's see how it. Let me see. Not really. Maybe I'll warm up a bit for Thomas's application by saying that we are building a demo ecosystem here in Aalto Industrial Internet Campus. It is of course a little bit limited now due to pandemic, but and also the building is under renovation. But we are building an ecosystem here where the virtual grinding machine would connect. Thomas will speak about this virtual grinding machine more, and how you can do like it in sort of like, let's say, hardware in loop type of configuration, where some part is really physical and some part is really virtual. That is something. The other thing we are doing here in the ecosystem, we are automating the crane operation, so that then we would have like a virtual part of factory here in Finland, which is then connected to abroad, so that we would have in this Machinaide project consortium, we would have a production in the Netherlands. Then we would have some logistic warehouse in Finland, and then the assembly line in Turkey. And this, of course, factory doesn't produce any physical real product, but it would show how you connect like different parts of your digital twins together and then run hardware in loop simulation. So and Thomas's presentation will tackle on this virtual grinding machine part. And now I would like to ask again, what is his status?
Yeah, I think we're trying, but maybe failing. I know there was a proposal here that we would be able to share his slides from our side and have the audio by phone, but Sylvia, I think, has that not worked yet?
Yeah, I don't see him. Thomas, can you hear us? Are you in?
I think Thomas can hear us, but not. Thomas, at the moment, your microphone is actually turned off. We could just try turning it on again and seeing if it works.
Do you hear me now?
Yes. Yeah, we hear you. Great.
And we see you.
Okay, we see you.
Got the normal connection working. Okay, I try to share my screen, so let's see what happens. I'm not very optimistic after these problems, but now it seems to be working.
Yeah.
Or do you see my screen?
We see your slides, yeah.
Do you see my screen?
Yep, we are seeing your slides now.
Okay, good. Then I'll start. And sorry for the slight problems in the beginning, but that's how it is sometimes with the virtual systems. Okay, so my presentation will be, as Kari already told you, about the virtual grinding machine, and I hope that you still can see it. Okay. Yep. So I am Thomas Widmeyer, that probably name you already heard a couple of times, and I'm working for Rolls-Royce International, and my topic today is the virtual grinding machine. But before we go to the virtual grinding machine, I speak briefly about normal grinding machines, real grinding machines. Our company, most of its turnover comes from grinding machine modernizations, and our main customers are in the paper and steel industry. And I guess most of you haven't seen yet a real grinding machine That's why I have here pictures of one grinding machine in a paper mill. The specialty about grinding machines in paper and steel industry is that they are quite large because the objects that are ground with them are also large. In paper mills, up to 12 meters long, 2 meters diameter, and in steel mills, slightly shorter, maybe 4, maximum 5 meters long. This is a typical paper mill grinding machine. Also from the other side, the yellow part, there is a measuring device to measure the geometry of the paper machine roll. The roll here in this machine is roughly 1 meter diameter and maybe 8-9 meters long. And as I said, we are getting most of our turnover from modernizations. In the modernizations, we have to also install quite many things and do commissionings and so on. And here is a new measuring device installed on the old grinding machine, some other new parts also. Then we do some commissioning on site. Here, me maybe 20 years ago on a grinding machine installation site. And of course, this belongs also sometimes lifting of heavy parts, like here the carriage of the grinding machine. That many other things happen on site. Here is a brief layout from an automation system, control system of our grinding machine. Of course, they vary a little bit from machine to machine, but this is quite basic layout. Then the common modernization projects that we have, the best one for us is the complete modernization. Then everything is modernized in the machine, both mechanically and electrically. All parts are overhauled or replaced with new mechanical parts. New devices can be added to the grinding machine, maybe measuring devices, balancing devices, etc. Then there are new electric cabinets, new motors, new control system, and so on. And because we provide all the parts, we can test them here at our site before we go to the customer. And that is very good for us. Unfortunately, many of our customers, they want to have a partial modernization. The most important reason for that is that they don't have enough money to the complete modernization, and they choose some steps from the complete modernization. For example, they want to have a new control system, but motors and electrical cabinets and so on stay from the old installation. And because of this, we cannot test the system before we go to the customer. That's why we want to have a virtual grinding machine so we can test it before we go to the customer. So now I go to the main part of this presentation, and the virtual grinding machine is actually a digital twin of a real grinding machine. And there are at least two possibilities to create a virtual grinding machine. First one can be seen here. So we have real NC hardware, and it operates in simulation mode. And then we have some other hardware that is used to simulate or to emulate the real hardware behind it. And then there is some software in the simulation module here. In this example, this is Siemens Sinomeric 840 DL SL numerical controller, and then the SIMIT unit is used to simulate. And then we have some software that simulates the hardware behind the machine or connected to the machine. The other option is that we have everything is simulated. We have an software that simulates the NC controller and the attached hardware. And one example of that is Siemens Sinomeric 1 virtual. It is displayed here in this part. And here, everything, you don't need any real hardware except a computer. And of course, both systems emulate or simulate a real grinding machine. And why we want to make a virtual grinding machine. And on this slide, you can see also the operators panel of the grinding machine. And we have already built some parts of the virtual grinding machine. It's not ready yet, but here you can see this is our virtual grinding machine now. It's much smaller than the real one. But the reasons why we want to have a virtual grinding machine is that we want to speed up commissioning and testing of the grinding machines with the help of this digital twin. And then we want to create more efficient tools for service. And we can do also software development without real hardware. As you could see from the pictures previously, a real grinding machine is up to 15-20 meters long and very heavy. And the price is, if you want to buy a new one, it's roughly 5 million euros. So we save a lot of money if we use this virtual grinding machine. So what the virtual commissioning and testing includes, so we can test practically all software with help of the digital twin. We can also make some kinematic models from the grinding machine and in its environment, but that requires 3D modeling, for example, Siemens NX or Technomatic plant simulation or some other software that is available. And you can test there on screen everything that the machine does. Then we can use the virtual commissioning also to find some potential weaknesses from the system before we go to the customer to do the installation. And of course, especially in the partial modernization, we can determine component compatibility. For example, if the customer has old components that he wants to keep, then we can test them in the virtual grinding machine if there are some simulation models available for these components. And also, we want to create new tools for service, new innovative tools. Some tools that have never been before, not by us or any other company. Then we can use the digital twin to solve problems on existing machines. If we update the digital twin based on the data collected from the real grinding machine, we can use this data also to create adaptive maintenance programs. For example, we know when it's time to do a service for the machine. We know when the motors are too old. We know when there is some defects. We can test this everything with the digital twin if we collect data from the real grinding machine. And one benefit is also that we can have live monitoring of our grinding machines worldwide if we have a connection to the machines. So this was my presentation, and sorry again for the delay. This was, I know, a brief introduction to the virtual grinding machine, and we will be working on this subject still further, but thank you for your attention. And I answer any questions you have, if I can.
Thanks, Thomas. This was great to have you here and get the lines working. There seems to be no question now. Maybe I'll pose a general question, like what do you think? What is the biggest obstacle? I heard you saying that you are doing something no one hasn't done earlier, and so what is the reason why this is now doable, whereas it wasn't doable some time ago?
Maybe one reason is that simulation software has developed quite a lot, and also one reason for this is maybe that the niche of grinding machine modernization, it's quite small part of the industry, so there are not many companies that do that, and Maybe one reason is also that the grinding machines, they are very important for the paper and steel mills, but from the management point of view, they are not so important because it's not really part of what the paper mill or steel mill does, even though the machines are important. That's why there hasn't been so much funding also for this kind of development projects. So the general knowledge about grinding machines is not very good in the industry, especially in the management and so on. That is one important reason why there has been so little research. And also the companies that work in this branch, they are normally not so big like our company. We have turnover maybe 2 million per year. So we don't have so much money to do extensive development and so on. And I think that includes also many other companies that work in our branch.
Thanks, Thomas. This was really good presentation to conclude our session, and luckily we got you through.
Good to be there.
Thanks. I'll move to Sam. Do you have some closing words? I do have some, but I'll give floor to you first.
Excellent. Thanks, Kari, and thanks to Thomas. That was really, really great and really worth waiting for. So yeah, just from my side to thank you to all the other presenters, and I think now Kari will say some closing words and mention that there's going to be a feedback question popping up at the end of the Zoom session. So please do answer there. But Kari, I'll leave the closing words to you.
Okay, thanks, Sam, for helping, and thank you. My deepest thanks for you all presenting here. Our organization team, this has been going very well, and most of all, thanks for audience, active questions and participation, and also like coming in. I know that you all have, let's say, enough these video conferences today, but thanks for joining us. Stay healthy. Remember to do outdoor activities, go biking, motorbiking, go out, whatever you can do in this pandemic time. Hope to see you soon face to face. I hope next time in our demo day you can experience our demos. You can touch our demos without we have to plunge them always in hand sanitizer and then give further. I think this would have been the case today if we had some demos. So we would have a barrel of hand sanitizer and then safe distances, etc. But I hope next time we have a cup of coffee and we see face to face. Now when you are closing the session, there is a feedback quiz. The questionnaire should be quite brief and quick to answer. We really hope that you have some time to answer on the questionnaire, so we can then improve our demo day and circus. And then the slides and by the presenters and the videos by student groups, they will be on Aalto website next week, and we will send the link those who have registered to this event. So big virtual applauses to us everyone, and thanks, stay safe and goodbye.